Right, sorry about the delay. So last time we discussed about this graph or network representation. And many algorithms and applications will utilize this form of an input information of our data. Okay, and so yeah, in terms of types of data mining methods, yeah, of course we have a supervised learning and unsupervised learning. And then in the case of an unsupervised learning, we know this clustering is one representative unsupervised learning type of a method, but also this density estimation and dimension reduction are also viewed as a unsupervised learning. So in the case of density estimation, we used the most basic method is a Gaussian mixture model, right? Gaussian mixture model, and this is a parametric model. But in the case of non-parametric model, also another famous density estimation method is called kernel density estimation. Okay. And also in the case of dimension reduction methods, we have a PCA and SVD, although SVD is not just used as a dimension reduction method, but it's also viewed as a low-rank matrix factorization method, and which has many different applications, but also multi-dimensional scaling. So these dimension reduction methods are also belonging to the category of unsupervised learning. And here I mentioned this Gaussian mixture model as parametric model, right? And this guy is non-parametric model, right? So does anyone know the definition or the difference between parametric and the non-parametric model? Can anyone answer? You can answer in Korean as well. What's the difference? Okay, so in the case of a parametric model, of course, this model must have a parameter, right? And then in the case of a non-parametric model, does it mean that they don't have any parameters? It is not. I mean, they also have their own parameters, but the main difference that separates these two is in terms of the number of parameters that a particular model has. Okay, so in the case of Gaussian mixture model, suppose we use 3 different Gaussian components, okay, in one-dimensional space, okay, and then how many parameters should we determine, okay? So each Gaussian will need 2 parameters, mean and the variance or standard deviation, and so we have 3 different components, and we need 6. Is that it? I mean, someone may be familiar with this Gaussian mixture model, but some others may not. But assuming that you guys are familiar with the Gaussian mixture model, then what are the number of parameters? I mean, we understand at least 6 different parameters, right? Where each of our Gaussian component has a mean and the variance, which are 2 parameters. And also, are there any other parameters in this Gaussian mixture? Weights or variance matrix. So here we assume our data is a 1D. So covariance matrix will just reduce to a single scalar value, right? So we are just dealing with the scalar. So for example, suppose our data is 3, 8, 5, 4, 4, 6, 7, 8, 9, and 2, -1, and so on. So these are the collected data that we have, and then we can fit our Gaussian mixture model using maybe three Gaussian components. So for example, yeah, intuitively in the 1D case, suppose these are our data that we found. Okay, and then intuitively we have one Gaussian component, and then the other, and then the third, and so the overall density estimation will be something like this, right? Okay, so we can fit this Gaussian mixture model based on maximum likelihood estimation, right? Okay, so in this case, each Gaussian or each mountain will have their own mean value and standard deviation or variance, and also as you can see, we have a different height, right, of the peak of this mountain, and this peak is determined, yeah, of course, based on a specific Gaussian. I mean, if one Gaussian has a narrow variance or the standard deviation, and then naturally the peak will be higher compared to the Gaussian, which has a wider variance, right? So still the constraint should be this area should be equal to 1, right? But at the same time, I mean, other than that, in this Gaussian mixture model, there are also parameters that will influence this height of this peak of each mountain, which are the prior, right? So this Gaussian has the prior probability of maybe 25% and 30%. And also for this, it's a 45%, right? So these are the prior probability assigned to each of our Gaussian components, right? But anyways, yeah, if you're not familiar with the Gaussian mixture model, and then it's quite intuitive, although the fitting strategy or technique is based on a little bit sophisticated or complicated EM algorithm, but yeah, at least you can understand like to model like multimodal distribution, or when having multiple peaks in our distribution, and then we can utilize this Gaussian mixture model. Okay. Okay, so in this case, each mountain will have a one mean and the one variance, and so it's 3, and so 6 parameters in total, and also we need this prior value, right? So we need 3 different parameters, right, for these, right? But at the same time, our actual parameters, considering the degree of freedom, will not be 3, but just 2. Because once we define 2 of them, and then the other one will be just defined as a 1 minus the sum of the other probabilities, right? So we actually have 8 different values to determine. Okay. So again, this one is a parametric, one class or one kind of type of a parametric model, and the reason why we call it as a parametric model is because they have their own parameter, but the number of parameters are not dependent on the number of our data. Okay, so think of our data. The number of our data is 100 or several thousands or millions. Yeah, regardless of that. Although if we use more and more data, and then this Gaussian mixture model and their estimate of these parameters will be more and more reliable or accurate. But yeah, the number of parameters to determine will remain the same regardless of the number of data items in this case, right? So in that sense, the parametric model will have the fixed number of parameters, not independent of the number of data items. So usually we call these types of methods as a parametric model. So in the case of linear regression or logistic regression, they are also parametric model, because I mean, in the case of linear regression, although the number of parameters will be proportional to the number of variables. So if we have 3 variables and then including the bias, so we have 4 parameters to determine. But whether we have only 10 data or hundreds of data, and so on. Yeah, these number of parameters, which are 4 parameters, will be fixed, assuming that we have a fixed number of dimensions. So that way we call it as a parametric model. In the case of non-parametric model, so does it mean that, for example, this non-parametric model has the number of parameters proportional to the number of data, or maybe inversely proportional, or something like that? So yeah, so we cannot clearly define non-parametric model. It's just like the relationship between rational and irrational number. So we have the clear definition of rational number, but what about the definition of irrational number? So all the real numbers that are not rational numbers are called irrational number. So 네, 유리수, 무리수 알죠? 유리수, 무리수를 다 합치면 이제 우리가 이제 실수, real number라고 부르잖아요. 근데 이제 거기서 이제 유리수의 정의가 뭐였죠? 유리수의 정의는 이제 뭐 서로소인 정수, 분의 정수로 나타내질 수 있는 그 정의가 이제 유리수잖아요. 그래서 뭐 다들 기억할지 모르겠는데 이게 뭐 루트 2가 이제 유리수가 아님을 증명하시오. 뭐 어떻게 하는지 아나요? 뭐 루트 2 이꼴 a분의 b 해갖고 ab 이꼴 서로소인 정수 해갖고 이렇게 해갖고 그거 제곱하면 2b 제곱 이꼴 뭐 a 제곱 해갖고 얘가 서로소가 만족이 안 되거든요. 그렇게 귀류법을 쓰면. 네, 하여튼 그래서 이제 하여튼 유리수는 그래서 클리어한 데피니션이 있지만 이제 무리수는 실수 중에서 이제 유리수를 만족하지 못하는 모든 애들을 다. 네, 그러니까 마치 이제 여집합 같은 개념이에요. 그러니까 명확한 정의가 있는 어떤 숫자들의 여집합을 이제 우리가 무리수. 무리수는 정의가 없어요. 명확한. 네. So yeah, similar to this case where we have no specific definition of an irrational number. Yeah, other than just saying irrational number is those numbers that are not satisfying those definition of a rational number. So in this case, yeah, to my knowledge, non-parametric models doesn't have a specific or clear definition, but yeah, it is just the older model that doesn't satisfy this definition of a parametric model, which is the model has the fixed number of parameters regardless of the number of data items. Okay. Yeah, and then what about the kernel density estimation? Do you guys know about the kernel density estimation? Okay, so the kernel density estimation works as follows. So still we consider 1D data, okay, and then those little vertical points will be our observation or our data sample, okay, and then for each data sample we assign a small Gaussian which are identical across all the data items. For example, if we have maybe 10 different data, and we assume a common Gaussian, just a single Gaussian model, but we just scaled it by 1/10, so that the sum of all the Gaussian components will be equal to 1 in terms of the total probability. Okay, and then similar to